Hello hires, we are looking at the problem solving question, data handling from the 2012 paper, question 10. Here's your context. Okay, French bean plants were grown over a period of 4 weeks in solution containing different concentration of lead ions. After this period, measurements of transpiration rate, dry mass and lead content were taken from plants grown in each solution. Okay, they then tell you that you're going to have 3 different sets of data, a graph, a table and a bar chart, and you get them all at the start, which is not the same as we've had for some of the other ones. So graph 1, we have the average transpiration rate in centimetres per metre squared of leaf per hour. Okay, centimetre cubed, sorry. So that's how much water is coming out from a given area over the leaf surface. It's a reasonably nice scale. This is going up in that's just ones, 1 meg per litre. This is going up in, we're going fives. Yeah, so these scales are not too bad, and then we've just got a line that we're working from. The table shows the lead concentration again, so the same kind of thing we had on the graph, but this is just obviously in the table. We've got the average dry mass of roots in grams and the average dry mass of shoots. Okay, at least we know what that is now. And then we have a bar chart, and this has got a secondary axis, so just to make it slightly more complicated. So we've got the average lead content of the roots going up the side here. So this is going up in ones, and it is this one that we're looking at. So this is the first bar graph that you've seen with a secondary axis. You've seen several line graphs of secondary. This is the first bar. So the roots one we are reading to this side. And then we also have on this side the average lead concentration of the shoots. So this one is going up in, where we're going, so that's 0.1, so 0.02s this is going up in, and we are reading all of these bars to this side. Okay, so watch out for that. That's probably going to be an issue. Okay, using values from the graph to describe the changes. Now you have seen these multiple times now. It's worth 2 marks. You're probably going to have to put 4 points on, and you're going to have to be careful about your units. Okay, so points we're going to have to put on. It says from 0 to 40, so it's the whole length of the graph. We're going to need this point. 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 This should not surprise you anymore. 4 points for 2 marks. Okay, so reading them off carefully. So we've got at 0 megs per litre. So you're going to have to put that unit in. Okay. You have, what did I say this was going up in? Fives. So where are we going? 5, 10, 15. No, we're going 5. So 60, 70, 80. Yes. So at 0 megs per litre, you have 180 centimeters cubed per meter square per hour. Okay, all of that, you're going to need all of that for a data point. Okay, and then it falls to 10 megs, and then it's at 150. Okay, with your unit preferably. It stays same to 20 megs per litre. Oh, just realised I missed the G, megs per litre. And then you've got falls to 40. And what have we got? 100 centimetres cubed per metre square per hour. I'm actually not happy with how I've written that. I would actually say falls to this, falls to that at 40 megs per litre, and it should be at that at 0 megs per litre, just to make it clearer, I think. But they're your data points. Okay. What evidence from the graph suggests that lead concentration is not the only factor affecting transpiration rate? Well, it has to be evidence from the graph, so you're going to have to look for an actual piece of information that you can pull from this. Here is your information. They increased the lead from 10 to 20 here, so that went up. The lead concentration went up along that line, but the transpiration rate didn't change. So something else must have been affecting it here, because an increase in the lead didn't make an increase in it, and that's what you need to talk about. Okay. Use information from the table to calculate the percentage decrease in the combined average dry mass of shoots and roots. See, whenever you see in bold, that's actually them trying to be nice. Maybe not feels like it, but genuinely is. Okay, so we're looking from the percentage decrease in the combined mass, so all of that from 0 to 40. Okay, so the combined mass here is 3.5 grams. And the combined mass here is 1.4 grams. Okay, so change divided by start multiplied by 100. So our change here is gone from, we're going 3.5 minus 1.4, so 2.1. So I'm just getting my calculator to do the actual calculation. So yeah, sorry, 2.1 divided by 3.5, actually it's a reasonable one, multiplied by 100 gives me 60%. Okay. Use information from the bar chart, we're going to need this then. Give the lead content of the shoots when the lead concentration of the solution was 10 mg per litre. Okay, so we're looking at the shoots. So this, they're really just giving you 1 mark for recognising that you're going to have to read to the secondary axis. 10 mg per litre, shoots here, this point, red to over here. So what do we say that was going up in? 0.02, so 0.04. That's it. Calculate the simple whole number ratio of lead content in roots to shoots for plants grown in a solution of 20 mg of lead per litre. Okay, again we're going to have to read to different axes, that's why it's considered to be tricky enough to give you as a system, you know. So here we go, here's our 20 mg and we're looking for roots. Our roots is at, we would say this is going up in 1, so 12, and our shoots, reading that way, is 0.3. Right, so we need a simple whole number ratio of this one. So I'm going to just divide them both by 0.3. So 12 divided by 0.3 gives me 40. And 0.3 divided by 0.3 gives me 1. So there's my concentration. That's it. And just to remind you, whole number. So you can't leave it, that's why you can't leave it like that. Lead content is expressed in mgs of lead per gram of dry mass. Explain the advantage of using dry mass rather than fresh. This is a kind, well, it's a reasonably common question. The bottom line is you cannot determine exactly how much water mass you will have in each leaf. So because it could vary, you have to get rid of it. So it's to avoid the fact that you have a variable amount of water in each leaf. That's it. Use the table and the bar. Table and bar, calculate the average lead content of the roots of the plant shown in the solution containing 30 mg of lead. So here's our 30. Average dry mass of the roots was 2 grams. Okay. Here's our 30. The average lead content. Where's our lead content of the roots? We're reading this way to here. So that's 25. So you had 25 mgs per gram, okay, and we had 2 grams. So 25 times 2, 50 mgs of lead. That's it. And here is your SQA Mart scheme. You'll notice that they are being very, very picky about units here, not surprisingly, and then everything else is pretty straightforward. Okay.